Alright, let's press on. Very annoying. Shh. The previous lecture recording failed, so I have to get Echo 360 and stick that on that. Very annoying. I'll give this one a go. It's so annoying. I've sat there, I've done little test recordings, works fine. I'm in here, do an hour, fails. Maybe I'll stop after half an hour and check whether I can save it. Alright, so we wanted to have a look at the difference between this and this. So here's the read version. Questions on that. That file descriptor 0 is standard input. We're reading into a tiny little character buffer of size 1, that one there. We're reading in 1 byte. And remember that read returns how many things it read. It's always going to return 1 until we reach the end of the file, and then it will return 0. So that's the control for that. And then we simply write out the character that we read in. Right, so that's compiled up, so let's through. Not sure why I'm timing that, but anyway, I just wanted to see that it's actually reading this file and scanning through it and writing it to standard output so I can send it through the pipe. Alright, so let's run it, except this time send the output to dev null. And we sit there and we wait 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 a bit longer and a bit longer. Aha! And finally we finish after 10 real seconds, but 1.8 and a fair bit of system time. Okay, so the output of this time command gives you the wall clock time, so it sat there for 10 seconds till we got our answer. It used a little bit of user CPU time, so just the time to run the while loop in the main program and so on, and a lot of the time was being used in the system, so making system calls, because read and write are both system calls. Right, so that's the other option to use get char and put char. Right? So read in the next character. Remember the reason we define this as an int is because EO is a character that corresponds to any char value. So on some systems it'll work defining that as a char, but generally it's safer to define it as an int. So once again, just reading characters from input, writing them to output. And interesting, there's something hogging a lot of CPU time at this point. Whoops. Right, so let's take a look. Just make sure, always, if you're going to do timing, you want to make sure that the program is actually working. So we'll do a very quick look. Yeah, it looks like it's printing out the stuff as before. That's good. Alright, that's kind of not relevant because I stopped halfway through. But what we did want to do was see how it takes to I/O this way. So it's reading the same file, writing the same output, so that shouldn't be part of the equation. Oh, big difference.
Are they doing like blocks or?
Yeah.
Yeah. Okay.
So get char and put char do buffering, whereas what we were doing before was effectively doing no buffering. I'm sure there's buffering going on somewhere. So that's the result using read and write, reading and writing one character at a time. This is the result using get char and put char. Obviously a big difference, and one of the major differences, so the user times to be about half, so kind of close, but it's the system time that's the real difference. Because there was 8 seconds of messing around with the system before, now there's 0.02, which is pretty much nothing. Right, the reason for that is that the standard I/O library does buffering. So it reads in big data and then dribbles it out to you character at a time simply by looking at a memory buffer. And when you reach the end of the memory buffer, it reads in another big chunk of data and keeps going like that. Okay? So the number of calls to read, there are still going to be calls to read here because ultimately the only way you can get data off the disk is to do a read call, but the number of calls to read will be significantly less than doing it this way. So, like for this, there was a read call for every single character in the file. I think the buffers in the standard I/O library are 8K, so there'll be size of file divided by 8,000 number of reads. So significantly less read operations. So that raises an interesting thought. What if rather than reading a single character, we read a large chunk at a time? Let's read 1,000 characters at once.
Optimal size? Or is that not really?
It would depend a little bit on the size of the operating system buffers, size of the disk blocks. You can fiddle around, we can try and see what difference we get. Need to be a little bit careful here because there's going to be a read eventually that has less than 1,000 characters, or there may be a read that has less than 1,000 characters. So if we say we want to write 1,000 characters here, we're going to, no, that 1,000 is fine, yeah, alright, so I should have a hash fine with in fact that's a fine idea, so I can fit in with it. Oh, good idea.
Does it read which size of like what it reads?
Yeah, it returns the amount of data that you read.
Yeah.
But if the size of the file is not an exact multiple of the buff size, then there's going to be, the final read is going to have, let's say, 500 characters. So if I just keep writing at 1,000 characters, I'm going to write out the 500 at the end of the file that I read, plus another 500, which is the rubbish left over from the previous read, which isn't quite helpful. So let's change this. And now rather than writing out 1,000, we should write the number of characters actually got in the buffer. Most of the time that'll be 1,000. The very last block of data that we read, it'll probably be less. Is that everything? Yeah, it is. Whoa. Makes me wonder what's going on. Right, so once again, let's just take a quick look, make sure it looks like it's still reading the same stuff. True. The other thing that we might want to check here, wow. Is that the tail end of the file looks kind of visible. Now, in fact, I don't know what the tail of the file actually looks like, I guess I could do. It looks about right. Yeah. So it looks like it's reading the file. So now what we need to do is do our test. Aha! Significantly faster. And kind of comparable. Now, of course, the other thing we should compare it to is CAT itself, which is the system version of the same thing. And it might help if I do time. Whoa, even faster. Damn CAT. Perhaps we could achieve something like CAT by making a buffer bigger. Make it 10. Good idea. There is an advantage of hash define. I only have to change it in one place. So which one do I want? I'll assume it's still working alright. 563. Aha! Better and better. Of course, I guess if we were insane we could make the buffer 1,000,000 and it would probably only do 2 reads to read the whole file. Right, but you can see that buffering makes a big difference to the performance, and overusing system calls is always a bad thing to do, so try not to do that. So, obviously that leads into the discussion of buffered I/O. So, using read every time, especially for a single byte, is not a good idea. And even saying that, it's not actually going to go to the disk and can get a single byte. It'll be getting that byte from a system buffer. So everything, these buffers are different levels. So even though the operating system buffers the input from the disk, the fact that you've got to do a context switch from the user program to running a system call in kernel space is a costly operation, and doing that too much is a bad thing. So standard I/O provides that kind of service. It gives you a buffer. And when you think about what file star is, it's actually a pointer to an object that contains, among other things, a buffer. Alright? And so it reads it in buff size, that's a hash defined as standard IO.h. We can have a look at that in a minute, find out what it is. And the user doesn't see the buffering. They just see, I can do a get char, I can read a character at a time. But underneath, this is actually what's happening. So first thing we do is we look whether we've reached the end of the buffer. So pause tells you the current position in the buffer. So 0 and moves along. So when you do a read, if pause is equal to buffer size, it means you've reached the end of the buffer. And you want to do another read, you want to get another character, you've got to read in another buffer full of data. So you do a read operation, you reset pause back to the start of the buffer, and then you keep going. And normally, the normal case, 1 in every 1 over buff size times, you will not do this and you'll simply do that. So you're just going straight to the buffer, grabbing a character and returning it to the user. So that's a very efficient operation. So you minimise the amount of time that you need to do reads. All right, so let's see how big is buff size thing. Hopefully it's. Oh no, this machine. I'm going to go to CSV machine. At least that puts the .h files in the obvious place. Thanks. Alright, so it's defined in terms of another value, which I guess I could try and find. Which will probably be in some other file. Yeah, as I said, it's in some other file. Right. Let's see if we can find which file it's in. Right. I give up. Somewhere there's going to be a hash define of score IO buff size to some number like 8. You can spend chasing down values in the .h files in user and conclude. And sometimes it almost looks silly. You got something defined as something else. But anyway, I think it's pretty much okay. How else could we work this out? I don't know how we could work it out. It was a bit cheating. Good. One, get it eventually. Oh, okay. 1,004. I thought it was bigger than that. Interesting. So our 10,000 buffer, 10,000 size buffer should have blown it away. And the fact that it didn't suggests that 1,024 is an appropriate size for the device that it's reading from. Interesting. Alright, so final thing to look at, well, let's see if we can re-implement. You know, we've done myLS, this week you're doing myShell, let's have a go at myStandard IO. So I'll just grab all of that. So what the user sees is the type file start. Okay, so like standard IO, but I don't need to include it. So gets in, puts E, should be able to write all right. Pretty much. Okay, so fopen is going to have to create one of these file objects and initialize it appropriately. So one thing we're going to need a file start. To allocate one of these file objects. Is that enough? It's not enough because buffer is defined as just a char star. So we've allocated a file object, but we haven't actually allocated a buffer for it to use. So we're going to need to do that as well. Here I'll just assume that it's going to work, that all the mallocs never fail. And here, how big do we want our file buffer to be? Let's make it 4K. So we just allocate 4096. Alright, the mode can just be what we entered. Oh, there's some critical thing I've forgotten here, actually. So we can just make a copy of that. That's what are we going to need? Yes, we need a handle on the open file. So what else? Alright, so new pos. So we can start at the start of the buffer. Right, so we've allocated a file structure, we've allocated a buffer to go with it. Now we've got to actually open the file and fill up the buffer. And now I'm cursing that I made mode as a char. Let's make it a char star like the real F open. So I'll just grab the first character. Oh, it's even worse. What is it? What is it? Is it? I think that's the way of opening it and getting a file descriptor. I think that's right. Anyway, at some point we need to do an open and we need to get back a file descriptor. Someone can check, see whether that. In fact, I'll check right now. Does that function actually exist? Bingo! Accepted. Open. Doesn't do what I want. It opens it. It takes a file descriptor and gives you back a file star. Yeah. Alright, so I think what I need to do is be a little bit let's do. Imagine we got a function that converts a mode into one of the O underscore modes, underscore read, O underscore write. That'll this version there. And in that case, maybe we can put it back the way it was as just plain old characters. So we just pass in a single character and we'll have something that'll convert that. Alright. Now I guess it's possible that the open fails. Maybe it might have been smarter to do that first, because we don't want to go to the trouble of creating all the object if it's not going to work. Remember, standard system caller returns a value less than 0 fails. And in that case, what does fopen return? Yeah, it returns null if the open fails. So we may as well make behaviour like that. So we can just give up. Otherwise, why don't what? And I'll return a pointer to it. So something that looks like what fopen does. Get C, right? We already saw something a little bit like get C. So we had if pos equals, should have done a hash define for the buffer size. If it equals 4096, then we've reached the end of buffer load of data, so we need to get another one. Actually another, Oh, you make it up as you go along, what you discover. What am I missing? Yes. Okay, because remember, one of these buffers is going to not necessarily contain 4096 characters, the very last buffer. So, we also need, as well as having position, so we need to know how many characters are actually stored. Maybe I'll call it the number of characters stored in the buffer. So, oh, we didn't actually do something back here. Whoops. One other thing we need to do. New. Maybe we didn't do it because I didn't have that. We need to read the first chunk of data. Into okay. That now. Right, so now down here, we shouldn't be checking if pos equals 4096. Most of the time it will be. All of the chunks of data that we read in before the last one. But I should be checking. Oh, in fact, it's FP, isn't it? Ah, what are you doing? So if pos is equal to the number of characters in the buffer, it means we've just gone beyond the last character. So we've come to the end of the buffer, so we need to fill it up again. So we do a read from the appropriate file descriptor into the buffer, so it's exactly the same as what we did up here. So why didn't I copy and paste it? Good question. So we've set in chars. The other thing that we need to reset is pos goes to the start of the buffer.
Shouldn't be called FP. Shouldn't be called FP and not new.
Oh yeah, thanks. No problem. Now it is. Alright. And the normal behaviour will simply be that we return go. So most of the time we call get, we simply grab the next character from the buffer. Occasionally we need to read the buffer full. Now the other thing that you can also think about for this is that I've got a buffer full of data and I'm simply moving through it. Potentially I could go backwards through it as well. Small problem is I try to go backwards when I'm at the start buffer, and I got to go back, but maybe if I had two buffers, then that wouldn't be such a problem. But if you go and look through the standard IO library, there is an ungetC function which will push back the last character that you read, or at least go backwards one position. Alright, what about putC? Similar kind of deal if so we need to do this if the buffer fills up, so we can't just check that. So if we've got a buffer full of data, then we need to, before we can add something new to the buffer. So we need to do write And then this time, rather than returning, what we're doing is we're storing into the buffer. So in fact, so remember, put Z doesn't return anything. Now there's an issue. What happens to the half full buffer when we've finished and we're not doing any more puts these? I would suggest that fclose is going to deal with that. So fclose should look in the buffer, see if there's anything still there, and write that out. Okay. We hadn't implemented fclose, so there you go. Now fgets. Now, turns out that when you're dealing with functions like this, it often makes your life a lot easier if you define some of the functions in terms of the lower level functions. So it would be much easier if we implemented fgets in terms of getZ. So it's called getZ until we read, until we see a character, then we stop. The other thing that I've done here is I've been into the order of the argument. It's always annoyed me that C file argument last, so I decided to put it first here. Alright, so we're simply reading stuff in scanning until we see a new line character, or until we bump into the end of the file perhaps, which may happen midway through a line if someone hasn't terminated the last line in the file. And that's an interesting one. I won't deal with that just yet. Right, so what we got to do into our buffer, we stick the character, and at the end, having put all of our character into the buffer, we terminate it. By a new line. Now, of course, I've omitted something here, that we're passing in the size of the buffer, so we don't want to allow more than max characters to be stuck into the buffer, because that's how big the buffer is, if we're telling the truth about max. So, what? Oh, CH I haven't defined, yeah, good point. Alright, now I have. So a couple of things here. One thing we've got to worry about is if we get into the end of the file. What do we do? I'd argue that we simply jump out of the loop, which we can do using a break. So I used the loop, I tried to simplify the loop control logic, so we're simply going to look for an end of line character, and any of the special conditions that might occur as we go we'll handle by direct breaks out of the loop. I always think that's the easiest way to do it. If Richard Buckland was teaching the course, he'd be absolutely appalled and say you've got to put everything in the while condition. Don't have breaks, they're evil, or something like that. Anyway, and the other thing, of course, we have to worry about So there's run out of room in the buffer, so we have to jump out. Is that correct? Yes. Now there is a problem here, of course, so I mean that's fine. That will make sure that as soon as we fill up the buffer, we simply jump out and terminate it by null. But what's the problem?
Max is less than or equal to 0.
Right, if someone wants to put weird stuff like that in, sure, we can handle that. Something like that. But I mean, you can't tell. They can tell that max is at 1,000 and the buffer's only 20 characters long, which is a potential problem. No, there is a problem here. If we get to this point, that's fine. We jump out of the loop because the buffer's full, and we terminate it by.
We don't find the line. We don't find the line.
That doesn't matter. I'm pretty sure semantic F gets is that it'll read up to a certain point, and then when you come back, it'll keep reading, and eventually it'll find a new line. Stop there. Now the real problem is that we've read a character at this point, and then we've discovered, oh, there's no room for that character. Oops. So if we make another call to F gets later, the character that we were at when we realised we'd gone too far is gone. Ooh, could do. That'd be one way. Interesting. Oh yeah, actually put it in here, you're right. Equals what? Good question. I'll try the value of null. So hopefully we're not going to be reading in null characters, although in theory that is possible. So if we come into this function and there's a character left over from before, then we need to put that character into the buffer. Right, that character is not going to be a new one, that's good. Actually, one thing I forgot to do here is, oops, I didn't put it, FP. Right, so if we come in, we've got a character in the last variable, then we need to put that into the buffer to start with, and then keep reading. Something else that came out was the fact that I hadn't initialized I. Let's reset it to that. No wonder we use the standard IO like we don't try to write it ourselves. And who knows, maybe there's still something wrong with this. looks kind of plausible. I'm just a little bit worried about using that as our indication that there's nothing stored in last, because potentially you can read in null characters from the input. And what would happen if that was the case? Under certain circumstances, if the character that we read here, when we were right at the end of the buffer, would be a null character, and we stored it in last, we'd come back in, the next time we did this, we wouldn't store null character in this buffer load, which is vague. But I mean, maybe we can use EOF or something like that. Yeah.
Couldn't you use like a number outside of capacity?
Yeah, that's why I did EOF, because in theory, outside the range. All right, how come no one's asking about this? You suggested it, so you're not going to ask about it. Right, so if you define a local variable as static, it actually hangs around between invocations of the function. So in effect it behaves more like a global variable, but with a scope that's restricted to that function. So no one else can see last, no one else can modify last, but it persists between calls to f. So that we call to f gets, we'll play around with last. If we don't call to f gets, the old value of last is still available, which is something that definitely doesn't with these kind of variables. Okay, so static local variables is an interesting kind of strategy to need in a few places. Right, so yeah, there was one final thing. We should have an f close where if there's any left hanging around and we write that out as the file closes down. Alright, I think that might be it. Indeed it is. Alright, so let's stop there and I'll go away and cry about the fact that ScreenFlow isn't working.